Okay, in week 5, we're going to take a look at one of my very favorite topics, which is regular expressions, a collection of special characters that you can use to search for various kinds of patterns in text, in strings in the case of Python, and also you can make changes to those strings using these regular expressions. We're also going to take a look at reading and writing data that's formatted according to various structures like comma-separated value or JSON or well, we'll see some examples. And then in the second half of this, we're going to take a look at a collection of methods that you can use for interacting with and modifying and searching through strings. Okay, so regular expressions is a sort of a mathematical style notation for describing patterns in text. Now it's not mathematical in the sense of using a bunch of numbers and decimal points and so on, but it is mathematical in the sense of being very precise, using certain operator characters in very careful ways, having precedence rules and so on. It was developed to talk about human languages by linguists, but in the 1950s and 60s, stolen by people developing programming language compilers, language grammars, parsers, lexical analyzers, and that sort of thing, to help create these programs to do interpretation and compilation of programming languages. Python has an extensive collection of functions and regular expression special characters that we can use for searching for and making changes in strings. Okay, we're going to approach these regular expression special characters in stages, starting with what are called the basic regular expression characters. Then we'll move on to talking about some of the extended regular expression characters. There are also Python language specific regular expressions that I won't get to just because we have a limited time. And I want to cover the things that are pretty much universal, not only in Python, but also R and Perl and various text editors and so forth. So if you learn the basic and extended regular expression characters very well, you'll discover all kinds of contexts, not just Python, that you can use these things in. Okay, well actually I want to display this table here on the right side. I kind of need 3 separate windows for this, but I'm limited to 2. So let me put my table of basic regular expression characters on the right, and then we're going to take a look at some examples on the left side, and I will toggle on the right side between this table of regular expressions and a Python program called Regex examples, in which we'll see those regular expression characters in action. Now, to illustrate how these regular expression characters work, I like to use this silly program. Well, this would be a very silly program indeed. This is a little poem, actually, stolen from Alice in Wonderland. I can get away with it because Lewis Carroll is dead and his copyright is no longer in effect. It has the advantage of being brief, being sort of amusing, and pretty simple so that it's easy to see which lines are being matched by the various regular expression characters as we discuss them. Okay, so in the context of a Python program, particularly this regex examples.py program, we're going to store the poem as a list of strings. Okay, and then we're going to use a for loop to search through each line in the poem. All right, so we're going to loop through that list of strings. This variable line is going to receive the value of each one of those strings one at a time. And I'm going to use this regular expression matching function called re.search. Now, re.search, re is a module for regular expression searching, and search is one of the various functions available within that module. If we search a string to see whether the string contains a regular expression pattern, then one of two things occurs. If the string does contain the pattern, we get back an indication as to where that pattern occurs. On the other hand, if the string does not contain the pattern, we get back the value none to indicate that there was no match. So let me show you in the Python shell how this regular expression search function works, and then we'll see what's going on with this while loop here. So let me pull up my shell. Here we go. So let's suppose I do a regular expression search for the pattern A in the string hello world. Now, skipping back to my table here for a second, ordinary characters just match themselves. So unless a particular character is one of the regular expression characters, then it just matches itself. And so in this case, the character little a just matches the character little a. We're looking for a little a in this string hello world. And because little a does not exist in hello world, we get back, oops, I gotta import my regular expression module. And try this again. I get back none. Now remember that none does not print, so let me set up a return variable to contain that. I'll say ret gets re.search. We're searching for little a in hello world, and if I print ret, we see that it does contain none. Now let's search for a character that does exist. So if I search for little h in hello world, now I get back something called a match object. I can ignore the inner details of the match object, but what I care about here is the span of the match. So the match starts at position sub-0 in the string, and it's one character wide. Okay, so this span here is giving me the details about where and how long the match is. If I do an re.search for w, then I get told, well, that's a character 7, and it goes up to, but not including character 8. Okay, so again, this is just a one character wide match. Okay, so what's going on in our loop is we're saying for each line in the poem, if the regular expression search does not return none, that means we must have found the pattern in the line, and we're going to print the line. So the upshot of this loop is we're going to end up printing all of the lines in the poem that do contain the pattern. All right, so onward ho. Now, the first regular expression character that we're going to special character that we're going to introduce is the caret symbol. And now I've just realized that I'm doing this. Let me get back over on this side. So we're going to introduce the caret symbol. And caret is what's often called the beginning of line anchor. It matches the start of the string. If I use this pattern here, caret capital H, what that's saying is I want to look at each line to see whether the line begins with a capital H. In my program, I've got that as my first example pattern to search for. And if we take a look at the poem, we can see that there are 3 lines where the first character is an H. Okay, there's how doth the little crocodile, how doth the little crocodile again, how cheerfully he seems to grin. Each one of those lines begins with, a capital H. There is an indented line here where the first printing character is a capital H, but that capital H is not the very first character in the string. The very first character in the string in that case is the space character, so it's not going to match. All right, so let's run this program. I'm going to press F5 to run this code. And there we go. We get the 3 lines that I claimed we should get. These are the 3 lines in the poem where the first character is a capital H. Okay, so that's the caret. Now, the backslash is used to turn off the special meaning of the very next character. So if I wanted to look, and there are no such lines, but if I wanted to look in this poem for a line that contained a caret, I would have to turn off the special meaning of the caret symbol by putting a backslash in front. Actually, the situation is not quite that easy, because recall that backslashes are used for other purposes as well in strings in Python. For example, if I say s gets hello \n world \t howdy. All right, that's dumb, I agree. But here I have \n, this pair of characters in my source code represents the new line character in the string, and \t here represents a horizontal tab character. So if I print s, I'm going to get a line containing hello. Then on the next line down, I will get world tab howdy. All right, so that's a couple of examples that we have used the backslash for. And if we want a literal backslash in our string, or if we want a quote in our string, we would say something like, oh, let me put a space character in here, and then \\/ gives me a single backslash. \/ single quote gives me a quote character. So now if I print s, I get hello, new line, world, tab, howdy, space, \\, space, single quote. And so \n is new line, \t is horizontal tab, \\, is \/ quote is a single quote. What that means, all that noise means, is that if I want to search for a caret symbol, I can't just type a \/ and a caret. I have to type 2 backslashes and a caret so that a single \/ is then passed into the search function to indicate that is a backslash in a regular expression that's turning off the special meaning of the caret. Now, if you didn't entirely understand what I just said, I'm not shocked. The problem here is that it's a nuisance, it's a mess, to have to remember whenever you're typing a regular expression pattern to double your backslashes all the time. In fact, if I wanted to search in this poem for a line that just contained, sorry, I don't mean just contained in the sense that that's the only character. If I wanted to search for a line that contained a backslash, I would have to specify backslash backslash to get one backslash, backslash backslash to get another backslash. This passes a pair of backslashes, which is a literal backslash as the pattern that I'm searching for. All right, so I need to type 4 backslashes in order to search for a literal backslash in the string that I'm examining. Now, off the top of my head, I'm guessing that you don't like this idea. So, fortunately, in Python, unlike R, by the way, in R we do have to actually type these 4 backslashes to get a single backslash. In Python, you can stick a little R in front of a string to create what's called a raw string. In a raw string, a backslash is simply treated as an ordinary character, not as a special character that escapes the meaning or suppresses the meaning of the next character. Okay, so in other words, we printed out hello, new line, world, tab, howdy, space, backslash, single quote. But if I did this string again and treated it as a raw string, the R in front means that none of the backslashes in here have any special meaning. So we now have a literal backslash character followed by an N. It's no longer a new line character. And we have a literal backslash character followed by a T. And then we have a literal backslash character followed by a literal backslash, and a literal backslash character followed by a quote. And here we have a stray single quote out at the end, so we're actually going to get yelled at when I hit the enter key here. Oh. Ah! Okay. Okay, interesting. Interesting. So, in the internal representation, what Python chose to do was basically to treat these outer single quotes as a pair of double quotes, and then to store internally in the string each backslash as a pair of backslashes. But if I print s, what I get out is a literal backslash and an N rather than a new line character, a literal backslash and a T rather than a tab character, then 2 literal backslashes and a literal backslash and a quote. All right. Well, the upshot is that even if all of that strange, recursive, nested detail didn't entirely make sense, the upshot is that henceforth, in our patterns, we're going to put an R in front to make these patterns raw strings so that we don't have to worry about doubling our backslashes if we need to use backslashes in our regular expression patterns. All right, well, onward ho. So we've looked at the caret, and we've looked at using the backslash to turn off the special meaning of the next character. So we could say backslash caret if we wanted to search a line to see if it contains a caret. By the way, I'm saying caret here. This is C-A-R-E-T, not not the vegetable. Other names for the same character include circumflex, or some people call it the up arrow, or the hat. All of those are names that people use for that caret symbol. Okay, so I'm going to call it caret. Well, our next regular expression character that we're going to look at is the dollar symbol, which is what's called the end of line anchor. If the dollar sign occurs last in the pattern, then that means that the pattern has to occur at the end of the line. All right, so if I search for caret dollar, what that means is that I'm searching for lines that begin with their end. In other words, lines where the beginning and the end are right next to each other and there's no characters in between. These are going to be the blank lines in the poem. So let's confirm that. All right, instead of, let me change this pattern here to caret dollar. And I'm just going to get in the habit of always having my patterns be raw, so I don't have to worry about whether there's backslashes in here or not. When I run this, what should be displayed is the blank lines, and it turns out there's three of those in this poem. Okay, there's one below the dashed line, there's one below the author's name, and there's one separating the two stanzas of the poem. Let's give this a try. And there we go. Okay, so I've got 1, 2, 3 blank lines have been displayed by that for loop. Okay. Now, the dot matches any single character. And let me show you some examples of dot. If let's just display the poem first. For S in poem, print S. There we go, there's our poem. If I say re.search for the pattern d.t in, well, I want to do this in a loop. So for S in poem, print re.search for the pattern d.t in the string S. I don't have any if test in here. I'm just going to print the result of searching each string for d.t. Now, dot matches any one character. So what I'm doing here is searching through each of these strings, each of these lines one by one, to see whether there's a little d followed by a character followed by a t. And let's see what we get. Okay. I only got one match. So most of the lines in the poem did not match. I did get a match on line 6, which is just slightly off the top of the screen. So here is the one match that I got. And this is D-O-T. So the dot is matching the O in this particular line. All right, let's try another example. Each dot matches a character. So if I say search for, oh, let's say, I don't know, E.R.H. There's probably not going to be any matches. This is probably not going to have any matches at all. Well, let me create something that I know is going to have a match. So L dot T dot L. All right, so this is going to look for a little L followed by a character, followed by a little T, followed by a character, followed by L. And that has a couple of matches. The match is the first 5 characters of the word little. The line of text, the string, how doth the little crocodile, occurs a couple of times in this poem. And so we're matching L dot T dot L. That is, the first dot is being matched by the I, the second dot is being matched by the T. Well, if I want to search for a literal period, I need to put a backslash in front to turn off the special meaning of the period character. And let's see how that goes in my poem. Actually, I have no literal period characters in this poem. So if I do a search for backslash dot, I'm going to get no output. All right? Because the only punctuation marks that Lewis Carroll used in this poem are a couple of exclamation marks. So I'm going to plagiarize and ruin his poem here by changing these exclamation marks to dot characters, literal dots. Now when I save it and run it, I do get those 2 lines that contain literal dot characters. Okay, and let me now put those exclamation marks back. Okay, so caret matches the beginning of the line, dollar matches the end of the line, dot matches any one character, and we can use the backslash if we need to or want to turn off the special meaning of any one of these characters and other regular expression characters as well. Now, square brackets mean to match one character from a set or from a range. And in this next example here, we're using square brackets with a range of characters, capital A through capital Z. Now, in the ASCII character set, which we're using on our systems, the capital letters are in ascending sequence. So capital A is immediately followed by capital B, which is immediately followed by capital C, etc., and then eventually we get to capital Z. And there are no punctuation marks or other characters mixed in between capital A and capital Z. So we can say capital A dash capital Z rather than typing out capital A, capital B, capital C, capital D, and all the way to capital Z. What this pattern means in the regular expression is that we want to look for a capital letter in this position. Now, the entire regular expression is looking for, starting with 2 spaces and then a capital letter. Okay, so Adobe Reader won't let me highlight those space characters, but I promise you that this pattern is caret, space, space, and then the square brackets to indicate that I want to match a capital letter. Let's try that pattern. So we're looking for lines that begin with space, space, followed by some capital letter. And that's going to give for us all of these indented lines from the poem. So we're going to get improve his shining tail on every golden scale, how neatly spreads his claws, with gently smiling jogs. Oh, those rhyme. Amazing. So let's confirm that. Yes, so we get each one of the 4 lines in the poem that begin with 2 spaces and a capital letter. Okay. Now, next we're going to introduce the star regular expression character. The star never stands by itself in regular expression notation. So it's not exactly the same as like a file name wildcard that you might use in a Unix shell or Linux shell or in the command.com terminal in Windows. What the star does in regular expression notation is to modify the meaning of whatever regular expression character occurs before it. And so let's say instead of this arbitrary character C, let's suppose we have the specific character little a, and we say little a star. Well, little a star means to match 0 little a's, or 1 little a, or 2 sequential little a's, or 3 sequential little a's, or 4 or 5 or 9 or 50 or 1,000 sequential little a's. Okay, so that's what the star means, is to match sequence of 0 or more occurrences of whatever the character in front of the star is. Now, in this pattern here on slide 7, again, I won't be able to highlight. It will let me highlight, I guess, if I do it all at once. So what I have here is caret, meaning the beginning of the line. And then I have space star. Okay, so space star means no space, or 1 space, or a sequence of 2 spaces in a row, or 3 in a row, or 4 in a row, or 9 in a row, or 1,000 in a row. I like to think of space star as meaning optional space. That is, there might be no space there, or there might be 1 or more spaces there in sequence. After that optional space, as with the previous example, we have a capital letter by using our square brackets A-Z. All right, so let's see that in action. Instead of space space, I'm going to have space star. Okay, so I'm looking for lines that begin with space star, which means optional sequential spaces, followed by a capital letter. And let's see what we get now. Okay, so now we get all of the lines with optional indentation. That is, we've got 4 lines in here. There are 2 spaces at the beginning of the line. But then the first character that's other than a space character has to be a capital letter. And because this is a poem, and because it's not an E.E. Cummings poem, the first character in each line is a capital letter. Okay. So that's the star. This next example is pretty straightforward. We've already talked about the dollar sign. Here I'm just saying E dollar, meaning to look for lines in the poem that end with an E. That is, where the E, little e, is the very last character in the line. All right, so let's try that one out. So this is going to be lines where E is at the end. All right, E is at the end. And I have 3 lines where the very last character in the line is an E. Okay. In this next example, I'm using square brackets one after the other. So the first set of square brackets is going to match some lowercase vowel, either a little a or a little e or a little I or a little o or a little u. Okay, so that's this example here, that we're matching one of the specified characters that we've written between the square brackets. All right, so we're going to match one of the lowercase vowels, and then immediately following that lowercase vowel, we're going to match one of the lowercase vowels. So we're looking for two side-by-side lowercase vowels. Now, they don't have to be the same lowercase vowel, all right? We're just looking for a lowercase vowel immediately followed by a lowercase vowel. So we can find things like little a followed by e, little o followed by u. Oh, amusing, I just noticed. I've never seen this before, but here I accidentally typed the u before the o. I did that without realizing, but it's totally fine because the order that you put those characters in between square brackets doesn't matter at all. You could say E-I-A-U-O, O-U-I-A-E. It doesn't matter. Any of the characters that are within the square brackets will be a possible match. Okay, so side-by-side lowercase vowels is what we're looking for here. Let's give this one a try. So A-E-I-O-U, A-E-I-O-U. Another thing I just want to mention is that there is not a space between the first square bracket A-E-I-O-U and the second square bracket A-E-I-O-U. If you put a space in here, the space is treated as a literal character, and so what that pattern would mean is I want to look for lines that contain a lowercase vowel followed by a space followed by a lowercase vowel, which is a totally different thing from looking for side-by-side lowercase vowels. So let's look for side-by-side lowercase vowels. And here we go. So we have tail and pour and cheer and neatly. Each of those is two lowercase vowels side by side. All right, now I'm dying of curiosity since I brought this up. I wonder if there are any occurrences of a lowercase vowel followed by a space followed by a lowercase vowel. No. Okay, so there are not. I was wondering, you know, maybe there was something like now I can't think of an example. So here we go. Zorro escapes. Took me long enough, but here we have an example of a lowercase vowel followed by a space followed by another lowercase vowel. But we don't have any lines like that in this particular poem. All right, next up we have another example of the dot, but this time the dot is being used together with the star. Now, dot matches any character, any one character. Dot star matches any sequence of any characters, including 0 characters. Okay, so dot star matches either 0 characters or 1 character, which might be anything, or 2 characters, which might be any characters, or 3 characters, which might be any characters, or 5 or 90 or 5 million, all right? So dot star in regular expressions is how you indicate that you want to match some arbitrary amount of stuff, including no stuff at all. Therefore, what this pattern is looking for is little a followed by anything, followed by little e, followed by anything again. Well, followed by anything, it's not the same anything, followed by I. So we're looking for little a, little e, little I in sequence, And we don't care what there might be between the A and the E or between the E and the I. Let's give this one a try. So A dot star means anything, E dot star for anything, I. And do we have lines that contain little a followed by little e followed by I? And we do. Okay, so let's check. We've got here's little a, here's a little e, and over here is little I. So we do have a little a followed by a little e followed by a little I. Now, the fact that there's another little e in here, we don't care. That little e is just part of the dot star. All right, here we have A, then we have the first dot star, which just happens to match this little t. Then we have E, then we have the next dot star, which matches everything up to the little I. So that line does have little a followed by little e followed by little I. Likewise, here we have little a, little e, little I. Whoop, just I. There we go. Okay. So we've almost seen every one of the examples here on slide 3. We've talked about ranges in square brackets. We've talked about just a set of individual values in square brackets. The last one that we have to talk about here is square brackets if you have a caret inside the square bracket. Now this is potentially confusing because we've already used the caret. We've seen that if the caret is the very first character in the pattern, that is the beginning of line anchor. However, if the caret is the first character inside of square brackets, what it means is that you're interested in matching a character which is not one of the characters between the square brackets. So it's inverting the test. And that's what we're doing here with this example, the second to last example on slide 7. The pattern, let me pull up my shell. This regular expression pattern, square bracket, caret, little t, close bracket, means to match one character. Square brackets always mean to match one character. In this case, we're matching one character that is not a little t. So any character in the entire character set will match unless that character is a little t. Little t won't match. We are also putting a caret, I have to erase some of this highlighting. All right. We are also, in addition to the caret t in brackets, we're putting a caret in front, which means the beginning of line. We're putting a $sign at the end, which means the end of the line. And we're putting a star following the square brackets, which means that we're interested in matching some sequence of 0 or more characters that are not little t. So to say that in summary, what we're looking for is lines that begin with some number of little t's, some number of non-little t's, and then end. The short way of saying that in English is we're looking for lines that don't contain little t anywhere. That will include blank lines, by the way, because blank lines contain no characters, and consequently that's a match because a blank line does contain no little t's. All right, let's try this out. We're going to look for lines that begin with 0 or more things that are not little t's, and then end. And let's save this and run it. Okay, now, as I said, the blank lines are matches. We've got 3 blank lines. Whoops, it's hard to highlight blank lines. But I've got 3 blank lines in here, which contain... change my window size. There we go. I've got 3 blank lines in there. I've also got the line of I've got the line of dashes under the title. I've got the line describing the author, which doesn't have any little t's in it. And as far as the poem itself is concerned, I've only got 1 line in the entire poem that does not contain a little t. Because if we look at the poem, we've got little, we've got tail, we've got waters, we've got two. Every single line in here contains a little t somewhere except for that 1 line of text on every golden scale. How would I search for a line that contains no lowercase vowels? Well, if I want to look for lines that contain no lowercase vowels, I would just say square bracket caret A-E-I-O-U. All right, now vowels are pretty important. So this is going to match 0 of the lines of text. Every single line of text in here contains a lowercase vowel. I will only get the 3 blank lines and the 1 line of all the dashes. Those are the only lines that don't contain lowercase vowels anywhere. Okay, so that is the set of basic regular expressions. So we've looked at the beginning of line anchor, the end of line anchor, dot that matches any 1 character. Dot is often used with star to mean any number of characters of any number of any characters. But star is also sometimes used with things like the space character to indicate optional sequences of spaces. And then we've got square brackets with a set or a range, meaning one of the characters within that set or range. And with the caret symbol, it means one of the characters that's not within the set or range. And backslash will turn off the meaning of the caret or the dollar or the dot or the square bracket and so on. All right, so that is the basic set. Now we're going to take a look at some of these extended regular expression characters here on slide 8. So, vertical bar means to match either the regular expression to the left of the vertical bar or the regular expression to the right of the vertical bar. And let me drop down to an example here on slide 9. With this pattern, we're looking for lines in the poem that contain how with a capital H or that contain Nile with a capital N. So let's give that one a try. All right, so I'm looking for how or Nile. And let's see what we get, if anything. Okay, so we have many lines that contain how with a capital H. 4 lines, in fact, that contain how with a capital H. And we've also got 1 line that contains Nile with a capital N. So we got a total of 5 lines that match that pattern. I want to point out that the vertical bar here has low precedence. What it means is everything to its left or everything to its right. If the vertical bar had high precedence, then by implication, what that would mean is that we're looking for capital H, little o, followed by either a little w or a capital N, followed by ILE. All right, but the vertical bar does not have high precedence. It has low precedence, and consequently, what we mean here is that we're looking for how or Nile. Okay, now we can use parentheses to match a regular expression and also to create a group containing that pattern. And the importance of groups is that we can then refer to those same groups later by their number. If I have one set of parentheses, that creates one group, which is group \1. If I use two sets of parentheses in my pattern, that creates two groups, and the leftmost one is group number \1, and the next and the right one is \2. And it's possible to have many sets of it's possible to have many sets of parentheses, and they're simply ordered from left to right, \1, \2, \3, and so on. So let's take a look at what we're up to here with this pattern. All right, we're using square brackets here to indicate that we want to search for a lowercase vowel. Now we're using parentheses to make that vowel that we just found a group, specifically group number 1. And by using \1 here, what we're saying is we also have to have exactly that same lowercase vowel again. So this time we are looking for two identical lowercase vowels side by side. And let's see what we've got here. Whoop. So we're looking for a lowercase vowel, A, E, I, O, or U. And then we're looking for exactly that same, whoops, forgot my closing parenthesis. And then we're looking for exactly that same lowercase vowel again. So, I think I've only got one match in this poem. Yes. So I've only got one line in here containing two lowercase vowels right next to each other. Let me modify our poem. We're going to add a blank line and then Alice feeds her aardvark some cool ants. Not very poetic, I will grant you. And actually, I should make these two separate lines. All right. So now, what? This is going to match feeds. I wanted to match aardvark. So Alice gives her aardvark some. I have to have this be legitimate English. Okay, so that's stupid, but here we go. And so now I have cheerfully, which is a pair of E's, aardvark, which is a pair of A's, cool, which is a pair of O's, and so on. So that pattern does match two identical side-by-side lowercase vowels. All right, let me repair this poem. I think I've wrecked it quite well enough. Okay, there we go. Now, in this third example on slide 9, I'm using 3 dots to mean that I want to search for some pattern of 3 characters. I'm specifying that that 3 characters is a group. Then I'm using $* to match any number of other characters that might exist, including no characters. And then \1 to indicate that I also require that same original pattern of 3 characters to occur again. So in other words, I'm looking for lines that contain 3 characters followed by anything, followed by those exact 3 same characters again. Let's see if we have any such matches here. So I'm looking for 3 characters followed by anything, and then those 3 characters again. And these are not always easy to see. Sometimes they are pretty easy. Here we have 3 dashes followed again by 3 dashes, so that one's pretty easy. Likewise, 3 spaces followed again by 3 spaces. And in this next one, you might spot the occurring twice. Actually, what the pattern is matching space th there and space th here, because that's the first pattern of 3 characters that is identified that occurs again. In the final line here, what we're matching is es space 2 times. So welcomes and fishes, we get es space there and we get es space there. In this final example on slide 9, once again I'm looking for 3 characters, but I'm creating a separate group for each of those 3 characters. So the first character is group 1, and the next character is group 2, and the third one is group 3. I'm requiring those 3 characters to occur again later, but not in the same order. Okay, I'm requiring the third character to appear first, followed by the first character and then the second character. And I'm using $* to mean I can match anything in between the first occurrence of those characters 1, 2, 3 and the subsequent occurrences of those same characters in a different order 3, 1, 2. Let's see if we have anything that matches that. So, three, 1, 2. Oh, I guess this comment doesn't have anything to do with anything anymore. Let me get rid of that. All right, so I'm looking for 1, 2, 3 characters, followed by anything, followed by those same 3 characters, but in order 3rd, 1st, 2nd. And these may be harder to spot. Now, the first 2 lines of output are pretty trivial. So we've got dash, 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 1, 2, 3. Then we've got dash, 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 3, 1, 2. Impressive. Likewise, space, 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 followed by space, space, space. All right, now what do we got here? Let's see. Oh, I've been doing this example for a while, and I always have trouble seeing it. Here we go. Here's characters 1, 2, 3, E space L. And here's character 3, 1, 2. All right, so we have E space L as my characters 1, 2, 3, followed by 3, 1, 2 a little bit later. This next one is quite easy. We've got HIS followed by SHI. And in this final one is similar to the How Doth the Little Crocodile. We've got N space E followed by E N space. Okay. Now, so that takes care of the vertical bar and the parentheses and backslash with a digit for some group, plus is a little bit like star, except whereas E star would mean any number of E's, E plus means at least one E, possibly more E's. Question mark, on the other hand, means optional. It means there might be either 0 or 1 of that regular expression. And to illustrate, one thing that regular expressions are often used for, in fact, this is one of the things that they were originally introduced into computer science for, is to recognize valid tokens in programming languages. Recognizing, what is a valid identifier, what is a valid integer, what is a valid string, what is a valid floating point number, and so forth. Well, what is a valid integer in Python? In Python, an integer has some digit between 1 and 9 as its first character, and then may have additional, whoops, I didn't mean to blue outline that one, may have additional digits between 0 and 9. So if a string is going to be a valid Python integer, it has to begin with a digit between 1 and 9, followed by digits between 0 and 9. Let me pull up my shell. Okay, so 1, 2, 3, 4 is a valid integer. 1 is a valid integer. 0, 1, 2, 3, I get yelled at about that. I just realized a bug in my integer matcher here, because 0, of course, is a valid integer. So that means we need to correct this integer recognizer. So what we need now is, well, I'm so excited that I found this bug so that we can talk about it. I need to find lines to begin with either a 0 or a 1 through 9 followed by 0 through 9 star. All right, so my desire here is to look for either a 0 or a sequence of digits where the first digit is between 1 and 9 and the remaining digits are between 0 and 9, if there are any remaining digits. This enables me to talk about a different bug, which I see regularly, because remember that the vertical bar has low precedence. And so when I think about the vertical bar here, what I'm actually looking for is patterns that begin with 0 or that end with a sequence of digits starting with 1 through 9 followed by 0 through 9, any number of those. All right, so to finally fix the last remaining bug here, I need to use parentheses here around the or. So I want to match a string that begins with a 0 and then ends, or that begins with 1 through 9 followed by optional 0 through 9s and then ends. So that's the correct pattern for matching a Python integer. Okay, and then similarly for matching a Python identifier, the first character has to be a letter or an underscore. Remaining characters can be letters, underscores, or digits. Notice that because either lowercase letters or uppercase letters can be used in identifiers, that I specify both of those ranges. The problem with trying to do something like this, if I were to say starts with, okay, well, I don't know much. Actually, I do know a lot. But let's imagine that I don't know much about the ASCII character set, but I do know in the ASCII character set that capital letters come ahead of lowercase letters. I might be tempted to look for capital A through lowercase z. The problem with that is that between the capital Z and the little a are about a half a dozen punctuation mark characters. So that range, capital A through little z, does include all of the letters. It includes all the capital letters, and it includes all of the lowercase letters, but it also includes a bunch of punctuation marks, and we definitely don't want those punctuation marks. So that's why we split it up and say, all right, A through Z in caps, or A through Z in lowercase, or 0 through 9. In this particular example on slide 10, okay, I wrote the little a dash little z first, and then the big A dash big Z afterward. It doesn't matter. The point is that I'm specifying the range between capital A and capital Z, or the range between little a and little z, or the range between 0 and 9. And that's how you specify three discrete ranges as being possibilities within square brackets. Okay. Now, if we want to match a Boolean, in Python, that's either true with a capital T or false with a capital F. Notice once again that I've used the parentheses here so that I'm not accidentally looking for lines that begin with true or that have false at the end. Okay, well, that takes care of regular expressions. Let's look next at formatted file types that Pandas allows me to read and write directly. I can directly read and write comma-separated value files, HTML documents, JSON files, XML files. If I want to store information in binary, that involves doing what's called pickling. What pickling does basically is to save space in the file that you're creating. Although, frankly, so much out in the world is in text now, XML or JSON or CSV files, that binary data is, well, except for things like sound and images, binary data is becoming less and less common over time. So I'm not going to bother talking about pickling, but we'll take a look at some of these others. All right, so to talk about these various formats of files, we need some test data to work with. I have restarted my shell, imported NumPy as NP, imported Pandas as PD, and what we're going to do here is to recreate the F5 data frame that we looked at back in Lecture 4, which is a 3x3 data frame of some random numbers drawn from a standard normal distribution. Okay, so we first used NumPy's random.randn function to generate a 3x3 arrays of draws from standard normal, that is mean 0, standard deviation 1. And I rounded those to 3 decimal places to make them easier to read. Here's what we had for A5. And then using A5 as the data part for our data frame, I also specified tedious, not very interesting, index labels and column names, R0, 1, and 2, and C0, 1, and 2. So having created F5, if we display it, there's what we see. Alrighty. Now, the data frame has within it the ability to write itself into a CSV file through the toCSV, to_CSV method. f5.csv is what I'll name this thing. And I hit the enter key and poof, it's done. Now, if I switch over to a terminal, I actually have a Linux-like terminal in which we can see that, yes, this f5.csv file does exist. And it was just created. It's 5:27 p.m. on the 15th currently for me. And here's what the file contains, f5.csv. All right, so we've got the column names in the first row and the row names and corresponding values in the subsequent rows. If I were to load that into Excel, I would be able to see that as a spreadsheet. Now, to read a CSV file, the opposite or inverse of to CSV is read CSV. The distinction here is that when I wrote the CSV, I gave my data frame as the current object on which to invoke this toCSV method. But in the case of read CSV, that's going to create a data frame from the CSV file on disk, and so I have to invoke read CSV within the pandas library module. All right, so I don't have a current object yet, so I can't say something like f5.readCSV. I have to say pd.csv. Let's get back to Python. All right, so f5 copy now, I'm going to say is pd.readCSV from that file that I just created. Notice, by the way, and actually a lot of them go off the side of the screen here, but read CSV has got about 50 options that you can use to specify various formatting characteristics of the input file. All right, let's just give the input file and see what we get by default here. So f5.csv is our input file, and f5 copy, well, we're going to hope that it looks the same as f5, but no, actually. Turns out that by default, when you read in a CSV file, the read CSV file assumes that the first line contains column names, but all the remaining lines contain data. So read CSV by default assumes that the string R0 is part of the data, and likewise the string R1 and the string R2 are part of the data. Since no column name was given for that data, R0, R1, R2, read CSV just invents this index name for that column. Okay, so this is not quite what we had in mind. We're going to have to use at least one of these options for read CSV. We're going to tell read CSV using a keyword parameter that the index column, that is the row labels, the row index, is found in column 0 of the input file. Okay, let's recall what our input file looks like. Okay, so column 0 in this input file, those are the row labels, and everything else after column 0 is data, except of course for the first line where we do have column names. So let's re-execute read CSV with this keyword parameter. All right, so we're going to overwrite f5 copy with pd.read CSV from f5.csv with I'm trying to find, here we go, okay. So the minute I touch my mouse, click my mouse there, this help message is going to go away. But here's the index call. That's one of the 25 or 50 keyword parameters that I can specify to help ReadCSV understand the format of the input file. So I'll say index call equals, come here, equals 0. There we go. Okay, so now I got in the same thing that I wrote out in the first place. Let's suppose that we have a comma separated value file that does not have any row labels. We do have column names, and we do have values for those columns in the subsequent rows, but we don't have any row labels. Let me create this f6.csv file. Okay, so I'm actually running on Windows, but I'm using a Linux style of interface. So I'm going to make a copy of f5.csv called f6.csv and edit f6 with the good old VI editor. And all I'm going to do in here is to delete those column names so that I have exactly what's shown for f6 on slide 17. Save that. So here's my f6.csv file that has the right stuff in it. And now, if we don't have row labels in the CSV file, then the default behavior of ReadCSV is exactly what we want. Or at least it may not be exactly what we want, but it will do something that makes sense. Let's put it that way. All right, so I'm just doing the default ReadCSV, and I get my columns properly named from the column names in f6.csv, and I get, by default, labels of 0, 1, and 2. All right, let's take a look at a sort of the mirror image example. This time, we have a file called f7.csv. We don't have any column names, but we do have row labels. So let's investigate that situation. All right, so I'm going to make a copy of f5.csv and call it f7.csv. Edit this guy. And this time we're going to get rid of the column labels. I'm also going to get rid of this last row so that what I have in my file matches what's on slide 18. All right, so here's f7.csv. And now back to Python and into f7, I'm going to read CSV. The file name is f7.csv. I do have row labels in the first column, in column 0. So I do need to use my index call equals 0 keyword parameter. And there are no column names in the file. I don't want 1.64 minus 0.612 and minus 0.528 to be used as column names. So I'm going to specify column names as another keyword parameter. C0, C1, C2. And now I have F7 with the row labels that I want and the column names that I want. And this, if you take a look at the documentation for ReadCSV, you can investigate what all the other 47 keyword parameters do, and you'll see that you have parameters available to help you read just about any kind of structure of comma separated value file that you would like. Okay. Now, it turns out, this time we're going to take a look at HTML tables in online HTML documents. It turns out that rather than resorting to beautiful soup, if the HTML is very cleanly structured in an online document, you can use a pandas function called read table. And that will read in all of the properly structured tables from the HTML document for you and bypass the need to use beautiful soup. Now, on the other hand, if the HTML document is not perfectly well formatted, then read table might fail and you might not be able to read one of the particular tables that you would like. In that case, beautiful soup will still work mostly, and so it's a little bit more of a robust tool for flogging your way through and extracting information out of a not quite perfectly formatted HTML document. Okay, so let me use read HTML. Whoops, sorry. Okay, this is a bug. Yeah, it's not read HTML, it is read table. I'm sorry. No, I said that absolutely backwards. It's not read table. So this is an error. It is read HTML, and that will read in the tables from the HTML document. So the example is correct here on slide 19, and on slide 20. This is incorrect. It should be read HTML. All right. So let's give this a try. And I really don't want to type this in manually, so I'm going to copy and paste. So my table list is going to be returned from pd.readhtml. And the URL for my table of interest rates has got this long name. So I'll copy the first bit and then copy the next bit. Okay, and then the final bit to get the URL correct and the closing parenthesis for my function call. And it takes a few seconds, but my table list has 8 items in it. And if you are, if you happen to remember anything about our beautiful soup example, you know that there were 8 tables in that document. Now, the particular document that we want is the T-chart table. So we can add some keyword arguments to this read HTML function call, saying that the table that we want is the one that has the attributes equal to T-chart. And within that table, we do know that the header is part of the table. That's the thing that starts with the word date and then has those abbreviations 1mo, 2mo, 3mo, and so forth for the various terms of the interest rates. The dates are specified in column 0 for each of the data rows. So let's do this read HTML again with these extra keyword arguments. Okay, so adders is T-chart. Header is row 0. And the index column, the labels for the rows, is column 0. And now I only got one table. Oh, I used the wrong variable name. Ah, silly me. Okay, so, all right. So I'm just gonna cheat here and go ahead and say rates df list equals table list dot copy. I can do a dot copy of a list with no problem. And now, if I ask for rates df list sub 0, that is going to be the table of interest rates for every trading day during the year 2019. Okay, and it's 250 rows long. All right. So, we went through some pain using Beautiful Soup to scrape this information. It's important to know how to use Beautiful Soup, so I won't apologize for the pain. But you can also, assuming that the structure of the table is correct, use this read HTML function within the pandas module as an alternative. A third style of file that you're very likely to encounter from various sources online, or perhaps on your local disk, are what are called JSON files or JSON files. And the structure of these things looks sort of vaguely Python-ish. JSON arrays look similar to Python lists. JSON objects are sort of like dictionaries. And strings and numbers are typically analogous to the str, int, and float data types. The web page, whoops, I don't want to actually go there. The web page, come on, leave me alone. The web page that describes the grammar for JSON objects is at json.org, and it's a very clean, very simply defined data structure. Let's save our F5 data frame into a JSON file, f5.toJSON, which is like 2CSV, except we want a JSON extension this time. And now if we go to our terminal and list the files, okay, so here is our f5.json file. And what we've got here is a dictionary, basically. This is a JSON array, or I'm sorry, a JSON object, in which C0 is mapped to this row, C1 is mapped to the second row, C2, no, I'm getting this upside down. So C0 is the key mapped to this column of values from row 0, row 1, and row 2. And then C1 is the second column of values mapped to that column of values from R0, R1, R2. You can see how dictionary-ish this is. Many websites out in the world provide JSON data that you can download. And actually, when I was first teaching this course a few years back, I was teaching it for our Adelaide campus, and I thought, oh well, let's try to get some Australian data. And Australia has a very, very nice website called data.gov.au, which contains data of all kinds, and it's been in beta form for years. I can click here and find out what data sets are available, and there are 90,000 and some data sets available. I can search for, oh, cool, interesting. Now, I have no idea why this is, but this also was true way back when I first tried this. The city of Wyndham, for whatever reason, pops up quite early in the list of available data sets if you just do a random search. And let's find out about Wyndham. And notice that all of these things, all of these 5 things we see here are JSON data sets. So Wyndham, 5,632 results for Wyndham. Footpaths, playgrounds, kindergartens, barbecue locations, public toilets, buildings, bike paths, stormwater. Now, okay, so way back when I tried this initially, the thing that randomly came out almost right at the top of the list was smart bins, and I didn't know what a smart bin was, so I thought I'd better check that. Wyndham City Smart Bins. It turns out that the city of Wyndham has trash bins with sensors in them, so that the city can tell centrally which of its bins are getting full. So let's take a look at the JSON here. All right, now I can download the file as a raw file, or I can use this URL to go and access the JSON, which because I am using Python, I want to go ahead and directly access that URL. If I click on it, I get this not very readable stuff, but if you know something about JSON, you can sort of figure it out. And what I get told are that there are 3 elements within this JSON structure. There's a type and a name and then features, and the features are the individual bins. So let's find, here we go, feature, properties, here we go. Okay, so the properties tell me where this bin is located, what its capacity is, what its fullness threshold is, which tells me what level it has to get to before it considers itself full. And in this case, the fullness threshold is 0.8. It has to be 80% full. And the status here is in services, so it's not full yet. Let's see. So I'm doing this at almost 6 in the evening in the US. I think they are about 14 hours different. So I think it's around 8 a.m. there. So it would be a little surprising if we discovered many of these bins to be full at that time of the morning. Anyway, we can suck this in to Python and step through it as a sort of hierarchy of dictionaries using a function called read_JSON. Let us do that. Okay, I want to get out of my browser back to, I want to get this URL, so I'm going to copy and paste this URL into, whoops, that's my regular expression poem. Whoops. I didn't want to maximize that, so let me find my shell again. Here's my shell. All right. So now we're going to say sbdf, all right, smart bin data frame equals pd.read_JSON from that URL. And I got it. So sbdf now has information about all of the smart bins. Whoops, wait a minute. Oh, that isn't. Oh, wait, no, it is here. It is here. It's just down further. It's just down further. All right. Sorry, I accidentally scrolled up to my interest rate table. But here we go. So here we have smart bin 0, smart bin 1, smart bin blah, 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 blah. There are apparently 31 smart bins in town. Or 32 actually, numbered from 0 through 31. So if I ask for sbdf's shape, it's got 32 rows with three columns in each row. Okay, well, I'm not going to break this down. I guess let's take a look at the columns. All right, so the columns are name, type, and features. And the index, which is the rows, as we see, goes from 0 up to but not including 32. Okay. Now, sbdf.loc is how I can access a particular row. Let me access row 0. All right, here's the information that we have about one of the smart bins. And the name and the type are not very interesting. Let me look at the features. So I'm going to add the features column subscript .loc sub 0 sub features, and there we have the features of this particular smart bin. And what I would particularly like are the properties of the smart bin. Okay, notice that the features is another dictionary. Type is the key for feature. Geometry is the key for all of this detail stuff. Properties is the key for where the thing is located, what its capacity is, what its status is, etc. Okay. And if we discovered that the status was full rather than in service, then that would mean that we should send a truck up. That would mean that we should send a truck around to pick that bin up. All right, so that's the first half of week 5. In the second half, we're going to take a look at a collection of functions for messing around with strings. And so I will dive into that in the next video. Okay, so this is part 1, which I'm going to upload and then going with part 2.